Hi, this is Mrs. Kinman, and in this video, we're going to be discussing different characteristics of graphs of polynomial functions. Now, up here, we have a graph of a polynomial function. In our previous video, we talked about how we can identify what type a polynomial function is by counting how many motions it has. So this one goes 1, 2, 3, 4. So because it has 4 motions, we know that this is going to be a quartic polynomial. But in addition to how many times it changes, there are lots of other fun pieces of information that we can find. We can determine that these turning points are either maximums or minimums, depending on their location. We can also identify these intervals on which it's increasing or decreasing. So we can say we know that these are the places where it increases and decreases, but this one is going to decrease from negative infinity all the way to 2. And then it's going to increase from -2 all the way up to 1, something like that. We can identify those intervals as well. We also can figure out what the domain and range are, where those x and y-intercepts are. There's so much information that can be told about a polynomial based on its graph. And we can actually use this graph to find out so much information when it comes to them. So we're going to talk about 8 important things here when it comes to polynomials, different characteristics that we can identify. So very first, or 9, I guess. Very first, we're going to talk about the type. Now, we've previously talked about the type of a polynomial function before. And what we're going to do is we're going to use this example here to go through all of these things. We're going to talk about what it means and how we can find it. So the type we've talked about in a previous video, it kind of determines what the highest degree of our polynomial is. Now, because this one moves 1, 2, 3, 4 times, we know that the type of polynomial that we have here is a quartic function. And that's based purely on that degree, which is awesome. Then the next piece we have that we're going to look at is increasing and decreasing intervals. Now notice how I counted how many pieces there are. In these places, we're either increasing or decreasing. We're decreasing if our function is going down. So imagine you're drawing it from left to right and you're looking at it. As we go from left to right, if it were like a little roller coaster here, does it seem like my guy is going downhill or going uphill? Well, if I'm going from left to right, he's going downhill here. So that's a decreasing interval. And so my decreasing interval, what we're going to do is we're going to write them in interval notation, which means that we're going to talk about where it starts and where it ends. Where does it decrease? Well, our decreasing is going to occur from when we start at -infinity, and we're going to keep decreasing until we get to this point. Well, according to my graph, that seems like it's probably at the point -1 that it decreases to. Now remember, it's impossible for us to reach infinity, so we always put a parenthesis there. And then it goes to -1, but right here we get to this point. At this point, and this point, and this point, those 3 points, we're not increasing or decreasing. Those are what we call turning points. So turning points are the place where we switch from increasing to decreasing and vice versa. So these are those points. So in this case, our point here, which seems like it might be at -1, 2, 4, 6, 7, -1, 7, that's one of those turning points where it switches. Now, I'm not going to always ask you to figure out to identify what exactly is that point itself, but to label where is that point on our table here. So because it's switching at -1, 7, I know that I'm decreasing from -infinity to 1. And notice how those are just my x values. So we care about the time interval that it's decreasing, or that x interval is kind of what we're looking at here. So this is always on our x-axis. So we decrease from -infinity to -1. Then we are increasing here from -1 until we get to about here, which is like 1/2. So we're going to increase from -1 to 1/2. And then we're going to go back to decreasing here when we get to from 1/2 up to, I don't know, you might say 1.5, because remember these are blocks of 2. And then once we get past this piece, then we are increasing the rest of the way. So we're going to increase from 1.5 until we get to infinity. Now notice how these all have those soft or those parenthesis brackets. And the reason why is because we're not including any of these numbers. It doesn't increase or decrease at any of those turning points. That's why they're called turning points. So our turning points here are going to be those 3 red dots that we're associated with. Now local maximums and minimums are related to our turning points. Our maximums and minimums are dependent on where the turning point is. So it is considered a maximum value if it's between an increase and a decrease in that order. So we're increasing and then it goes to a decrease. So it's going to look something like this. That's our local maximum. A minimum, on the other hand, is going to be between a decrease and an increase. So it's going to be down at the bottom. And that seems to make sense, right? A maximum is at the top, a minimum's at the bottom. Now we call them local minimums and maximums because this is a great example on this graph here. Notice how really our function goes on forever in both directions. So in this case, that -1, 7, and our third point over there, 1.5, those two values are both minimums, but that -1, 7 is the actual minimum. That's the lowest point that our graph reaches. However, if we have an odd degree function, like a cubic function, notice how this goes on forever in both directions. So there's not really an actual maximum or minimum. That's why we call them these local points. Now, the other piece that we want to talk about here on this graph before we go on the fifth item is our x-intercepts. Now, x-intercepts are often also called solutions. You might hear them as being called zeros, and that's because they tell us a ton about our function itself. But really what we're looking for here is where does it cross that x-axis at? And so what we have here is it crosses our x-axis, or our x-intercepts are at the point -2, 0, and 1 in this case. And knowing 1 and 2, and knowing how many x-intercepts there are actually tells us a lot about our function. According to the fundamental theorem of algebra, which is something we'll talk about later, at most, a function will have the same number of x-intercepts as the degree of the polynomial. Now, it can have less, but it can never have more. So if we know this is a quartic function, that means we can have up to 4 x-intercepts. And we can also use that idea to then write the equation, which is super cool. Now, that there is 5 of those things. There are a few other pieces or characteristics that we're going to identify here. One of them is our y-intercept. Now, that is something, in case you forgot about our x-intercepts, the solutions are 0. Those are where the function crosses the x-axis, in case you were trying to figure out where those numbers came from. Our y-intercept, then, is where it crosses the y-axis. Now, it crosses the y-axis at only one point, and that's by definition of a function. A function can only have one y value for every x value. So it's only going to cross right here at this point. And so in this case, our y-intercept is at the point 0, 0, or when x equals 0, right? That's where our y-intercept is every time. So that's kind of one piece. Our next piece is called the end behavior. And this is what happens after it goes off the graph. So our end behavior is what happens when it goes off our graph. What is our function going to keep doing? Now, the way that I like to look at end behavior is I like to imagine I'm drawing this line past where it's going right now. If I were to continue this line on my graph, let me pull my graph down here. We'll take our little dot with us. If I were to keep drawing these lines, notice how I would draw this line up and I would draw this line up. That's because our end behavior is that our function is going up. If I had a function that looked like this, then our end behavior would be down on one side and up on the other, because that is the direction that our arrows are pointing. So it's not where it's increasing or decreasing, but it's that direction that the arrows are going that we care about here. So that end behavior, the way we write it is we say as x goes to -infinity. So as I'm looking at the left side of my graph here, so as I'm looking at the negative x values, where does my y value go? Well, in this case, it's going to go to +infinity because I'm drawing it up. I also look at what happens on my graph as I go more positive. So as I continue on drawing this way, as x gets bigger, what does y do? Well, generally, as x gets bigger, y also gets bigger in this case. Now, with that function down below, that blue one that was drawn, in that case, on our left side, or as x gets smaller, our y values, or as x gets more negative, our y values also get more negative. And as x gets positive, our y values get more positive. This is not like all the time, but it's saying in general what happens. Now, the very last pieces that we're going to talk about here are domain and range. So domain, remember, is what are the possible x values that work. And in this case, and basically any case with a polynomial function, the x values that will work here is actually going to be all the real numbers. So we either will write it as all the real numbers, or you might see somebody say that it goes from -infinity to infinity. I can put any x value in and get a possible y value out. That's the cool thing. Now, when it comes to the range, this is what are the possible y values that I can see. And this is super important. If it is an odd degree, then what happens with our range is it's actually going to be all the real numbers. Because if our degree is odd, then our end behavior is going to be 1 up, 1 down, meaning I can get any x value and any y value. However, if my degree is even, then what I need to do is it's going to either go from the maximum value, it's either going to go from -infinity to our overall maximum value, or it's going to go from our minimum value to positive infinity. So for example, with this graph that we have here, this right here is our maximum, or is our minimum value, right? Past here, the function just doesn't exist. And so this is the y value of 7. So what happens with an even degree, so in our case here, our domain is all the reals, but our range is actually going to be from -7 to infinity, because we have this minimum degree there, this minimum point, this true minimum. If we only have locals and no true minimum, then our range is going to be all the real numbers. So again, odd degree, our range is all the reals. Even degree, that means that it's either going to go from -infinity to the true maximum, or from the minimum to to infinity. So those are some characteristics of graphs. I would recommend that you check out some other problems in which you might do this. So you can take a look at any polynomial graph and identify these 9 different things. If you have questions, feel free to reach out, but those are different characteristics that we can identify from a polynomial graph that can then help us learn more about our polynomials.